Welcome back. So, let us continue the discussion of the statistical turbulence, and we are looking at the simple jet flow and looking at the solution. So, this is what when we derive the governing equations for the with the assumption like mean two dimensional flow and statistically stationary system. Now, we can find out the look at the mean flow solution procedure. So, the mean flow solution procedure, so we will do by order of magnitude analysis. So, then what will happen, we can further simplify the governing equation. Then we require self preservation and find expression for both, this is the half width and the u naught, and then we can solve the resulting differential equations, and we can see the assumption that we had. Now, first thing is that order of magnitude analysis 1. So, we can see the different length scales of variations in the flow. So, one of these that del y is y by to the power y half and del x which is 1 by L. So, that y to the power half and dy by dx. Then this is my length scale. Now, we can look at the velocity scale also. So, u would be order of u naught, u prime, u j prime, that would be order of u star. So, that is u star is, one can think about it is a typical velocity scale of eddy. So, velocity scale of eddy. Now, we can have some assumptions, and like number 1, y half by L is very small, which means the streamwise evolution of the jet is quite slow. Second, the Reynolds number u naught y half by nu, which is greater than L by y half. So, which clearly tells that at the large RE, so the viscous effect is quite negligible on the flow. Third is u star by u naught is order of y half by L square root of that, which means the turbulence adapts itself to changes in mean flow. Now, we look at the order of analysis 2. In that case, from continuity we can write that V bar is order of y half by L u naught, which is quite smaller than u naught. Now, we can estimate the terms in the y momentum equation. So, that means u bar del V by del x would be order of u naught square by L y half by L, where V by del y would be order of u naught square by L y half by L, and 1 by rho del p by del y would be order which is actually not known a priori. Then the diffusion component by del x2 would be order of u naught square by L y half by L square nu u naught y half, which is quite smaller than u naught square by L y half by L, which is cube. then the other component like y2, which is order of u naught square by L nu by u naught half order of y half by L, and u prime v prime by del x, it would be order of u star by L, which is order of u naught square by L y half by L. And last term, that v prime by del y would be order of u star square by y half, which is order of u naught square by L. Now, the required balance of leading term using assumption 1 would get us that 1 by rho del p by del y minus del v b prime by del y. So, we can now move to at the third level. Now, we have a simplified y momentum equation, which is now p prime by rho is p infinity by rho minus v prime, which essentially give me 1 by rho del p by del x equals to del v b prime by del x. Now, if we substitute this one in x momentum equation, we get u plus v v prime minus u prime by del x plus nu del 2 u by del x 2 plus del y 2. Now, if you do this estimate the terms in x momentum equation using assumption 2 and 3, we can get rest of the orders like u bar del u bar by del x would be order of u naught square by L, where v bar del u by del y would be order of u naught square by L, and v bar prime minus, which is order of u star square by L u naught square by L y half by L. Similarly, one can find this, which would be order of u naught square by L y half by L nu by u naught y half, which is order of and the other term in the diffusion equation. So, which is also, now we can see by del y, which is order of u star by y half u naught square by L. Now, the last part is that, so now we require the balance of the leading term. So, the stream wise advection is u bar del u bar by del x plus v bar del u bar by del y, which would be del u bar v bar prime by del y. So, this is streamwise advection, this is lateral advection, this is lateral turbulent diffusion. Now, this can be solved along with the continuity equation, which is del V bar by del y equals to 0. So, these two should be solved, then we get the self preservation. So, we can introduce some stream function that automatically satisfy mass conservation, where psi is u naught y half and f xi, where xi is y by y half. So, that means I can have mean velocity profile is u naught f prime xi, which is u naught small f xi. Now, similarity solution for turbulent stress, which is from the again experimental observation, which will give u bar v bar prime is u naught square g xi, and if we establish the relation between f and g using the Boussinesq hypothesis, so that is give us that g is 1 by RET f prime, where RET is u naught y half by nu t. Now, this guy must be constant in x if flow is self preserving, which means nu t should be u naught to the power half, and also turbulent viscosity is assumed to be constant in y. So, then my self preservation 2 would provide me, substitute the self similar solution into x momentum equation, will get me y half by u naught du naught by dx f square minus 1 by u naught by dx f prime f 1 by RET f double prime. Now, this will be self preservation if y half by u naught du naught by dx equals to constant and 1 by u naught du naught y half by dx is constant. So, which follows that y half would be s of x minus x naught and u naught is a into x minus x naught to the power n. So, s is tangent of spreading angle. So, this is tangent of spreading angle, and where n is the exponent n is undeterminate. So, we need an extra equation. So, this is undetermined. So, need extra equation for that. Now, we will get extra equation for u naught from integral equation for x momentum equation. We can get y equals to minus infinity to infinity del x dy minus infinity to infinity by del y dy minus y equals to del u bar v bar by del y dy, which is 0. Now, the streamwise momentum flask is conserved. So, we get m is minus infinity to the plus infinity rho u bar dy u j square d, which is constant, and m equals to half minus infinity f square d xi equals to constant. This will be also self preserving if u naught square y half is constant. So, the solution which we will get for the u naught is u naught a x minus x naught minus half, where Reynolds number is u naught y half by nu, which is a s nu x minus x naught half. So, this increases with s. Now, the solution of the resulting equation, which will give you the 2 alpha square f square f prime f equals to f double prime, where alpha square is 1 by 4 AC RE. Now, we can get f square plus f prime f half f square prime, and we get alpha square triple prime. So, alpha square f square equals to f prime plus c1 xi plus c2 xi. So, here c1 becomes 0 because of symmetry, and f prime 0 is 1, f 0 is 0, which gets c2 equals to minus 1. So, the solution for capital F and small f, capital F would be 1 by alpha tan hyperbolic alpha xi, and small f is 1 by alpha xi. So, the definition of jet half width f1 would be half, which is gives us back alpha equals to 0.88. So, we can see for a similarity solution for a plane turbulent jet, we can see how A varies. This is the profile of u by u naught. This is for turbulent Reynolds number of 31. So, this gives you an idea how things vary with. Now, at the same time, this non-dimensional velocity, this is how it varies, and this shows that. Now, this will give you an idea about the scale similarity of the round jet. So, here the Reynolds number is 1500, here 20,000, this is 200 million, and again the similarity means there will be similarity of the large scale structure, but once we go from this side to this side, the range of small scale structure actually increases. So, this is again some of the pictures, like this is mixing layer, jet, wake, this is the turbulent wake behind a sphere. So, this shows the self preservation, this is a high Reynolds number, this is a low Reynolds number. So, these are all example of self preservation of the system. Now, we can see what happens. So, there is a circular cylinder or a circular obstacle here, this is the, and this is a behind the wake, the flow field takes on this kind of profile, which is also. So, there is a, so this supposed to be my velocity, but because of this pattern, so there is a deficit. So, this is a velocity deficit at the center line in the wake, and this is the half width what we get. Now, when you talk about the self preservation, and this is what y by y half, if we plot, this shows nice plots, and this is how the wake behind that, the fluctuating component, how that behaves. So, this gives you an idea. I mean, there are flows which essentially shows this kind of self. Now, coming back to that, we had a mean flow in 2D. So, we got rid of this term, this term, this term, this term, because of the flow is statistically stationary and flow is statistically homogeneous in z direction. So, that takes out this particular equation. So, this is the equation we started off. So, now we find out the solution of mean velocity profile in the wake. So, we will again start with order of magnitude analysis and then simplify the governing equations. We find out the self preservation and solve the required equation, and once we do that, we can get the solution for the mean velocity profile at the wake. So, this is how we proceed for the. So, one can go through this in standard textbook and all this. So, we can come down to the ordinary differential equation that you get. So, this will give you an idea about the solution, which would be of minus alpha f plus xi f prime f double prime, where alpha is u c b RET by 2a, and with f plus xi f prime is xi f prime, we get alpha xi f prime equals to f double prime. So, we get alpha xi f equals to f prime plus c1, which goes up, c1 equals to 0, because in the limiting sense f xi would be xi, and solution of f, which will be c2 exponential minus half alpha xi square. So, that takes you f0 equals to 1 and f plus minus 1 equals to half. So, gets you a solution f xi equals to exponential of 693 xi square. So, if you again plot, so this is a similarity solution of a plane turbulent wake. So, if we plot that, then you get this kind of profile. So, this standard calculation one can continue and basically derive that. So, this is a solution of the f. Now, if you look at this particular picture, here is the UC coming in and you can see the intermittency near edge of the wake. So, gamma is the probability that flow at xt is turbulent, where nu t is like that. Now, if you have an axisymmetric round wake, then the solution of US and R half, you can find out the solution of this pattern. So, Reynolds number decreases with x, turbulence dies out of large x. So, it is a relaminarization. So, limited range in x where self similarity may be expected. So, that is now we can look at the scaling of wall bounded shear flows, wall bounded shear flows. So, we can take an like this, where this is the center line, there could be a nice velocity profile. So, this is u bar y, let us say minus dp bar by dx, this is x, this is y, this is delta, and this is u naught. So, profile for total shear stress, which will give me rho nu del u bar by del y minus rho u bar v bar prime, rho u tau square 1 minus y by delta, where rho u tau square would be tau w equals to minus delta dp w by dx. So, scaling of mean velocity gradient based on dimensional analysis, one can get y by u tau del u by del y equals to function of y by delta v and y by delta, where delta v is the nu by u tau. So, we have three different layer. One is the inner layer, where y by delta 0.1, this is close to the wall and length scale delta is not that important. So, what we get equals to f w y plus, where u equals to u bar by u tau and y plus equals to y by delta v. So, this is called law of the wall. You go outer layer, where y plus greater than 50, this is far from the wall, then we get u naught minus u bar by u tau is f d y by delta. This is known as velocity defect law, and there could be a overlapped region which we can identify, which is y plus greater than 50 and y by delta 0.1. We have 1 by kappa ln y plus plus b, and we have u naught minus u bar by u tau minus 1 by kappa 1 by delta plus b 1. So, this is derivation. So, this is one can think about log arithmetic law. So, once you put that thing, so there would be inner layer, log layer, overlap region, outer layer. So, these are the scaling region. So, this is adapted from Pope. So, one can go through the details there, and this is variation with the Reynolds number and y by delta. So, that is what you get, that when you look at these different scaling at the different region in a wall bounded shear flow. So, we will stop today and continue the discussion in the next lecture. Thank you.